Okay, so we're going to look at indefinite integrals today, which is section 5.4. We're also going to look at some definite integrals too. It's just a matter of looking at how they differ, and there honestly isn't that big of a difference between them. The biggest difference is what you actually get as an answer. So a definite integral has the values on the top and the bottom, which is your interval you're looking at, and your answer is going to be a specific number answer out. So when you have a definite integral, you're going to get a number out like 25 over 2 or things like that. You're going to get an actual value. An indefinite integral, you're going to get a function out. Indefinite integrals always have to have your plus c at the end because it's a family of values. Unless we give you information to be able to figure out that c, you have that plus c there. If you look over here, the only difference between this and what you saw last week when we did the definite integrals is there's a plus c after all of them. That's actually the only difference in them. Every other integration is exactly the same as the other ones were. So there's nothing new there that you need to necessarily write down. All right. So let's look at a few. So remember from last week we were talking about how addition and subtraction, you can just split them up and do them individually. So in this one, if we're looking at the integral of 10x to the fourth, remember the x to the fourth becomes x to the fifth divided by 5. And then minus 2. And secant squared, if I remember right, was tangent. And that's tangent of x. And then plus c. So you're doing each individual piece. So that becomes that. And that becomes that. Individually. 10 divided by 5 is 2, so we get 2x to the fifth minus 2 tangent x plus c. So that would be my derivative or integral. So like I said, the only difference between what we did on last Thursday was we had actual values at the end. That's it. Like, it's really not that difficult yet. Right? That's literally all you're doing. That's integration. And if there was numbers there, you'd plug the numbers in and get the answer. So. All right, let's look at this one.
So won't that be minus now? Because it's division? Or no?
Minus. No. So the hardest thing for integration is just like the hardest thing for differentiation. It's how do you change the problem to get it into something you can do? So in the last problem we had subtraction, which is fine, we can split it up. You don't have a rule for division. So we can't do just the derivative, the integral of the top, the integral of the bottom. It doesn't work that way. So we have to somehow change this to something that I can work with. So, and that's where things become a little more complicated. How would you like to go about changing this problem? So if we look at, so this is one of those things like you don't have, like in derivatives, you have a lot of different rules that you guys can pull on. Right now, you don't really have a lot of rules that you can pull on. So we really have this. So if we're looking down, we have a derivative, or I mean a trig function here. So let's just look at the trig rules. So there's my trig rules. Those are the only ones I have. I do have some in here. First of all, I have none that are in division, so that's not going to help me. But I do have a few in here that have multiplication. So is there some way that I can change this to a multiplication? Yes. What?
Break up the sign and then turn one of those into a cotangent, and the other one turn into
Yes. All right. So if we're looking at these, we have secant, tangent, and cosecant, cotangent. So right now, somehow I've got to get a tangent or cotangent in there somehow. And those are basically sine over cosine or cosine over sine. And this one, I can change that to cosine over sine times 1 over sine. Are those, is that the same? Yeah, because sine times sine is sine squared, cosine times 1 is cosine, right? Okay, so now cosine over sine is cotangent, and 1 over sine is cosecant.
Okay, can you repeat that?
Well, tangent is sine over cosine, right?
Oh, yeah.
So cotangent's the reciprocal of that. So it's cosine over sine. And then 1 over sine, the reciprocal function states that 1 over sine is cosecant. So in that case, I now have that interval. So the answer to this question is negative cosecant of theta plus c.
Negative, where you got that from?
That's the rule. So that's like at the beginning, that's really the hardest part. Is that you only have so many rules that you can work with. So, and even after we look at the stuff on Thursday when we start looking at substitution, which depending on how fast I get through this, I might actually start that tonight. So even if we're starting to look at the substitution, it's just like the chain rule, where it's just a function inside of a function. So you're still going to basically do a very similar thing to what you're looking at now, until you get into Calc 2 where you have your other integration rules. Yes.
Multiply it by 1 over sine because it's sine squared on the bottom.
Yeah, basically I just took the fraction and split it up.
Okay.
Yeah, I just took the fraction and split it up. So what you typically would have done is taken those two fractions and stuck them together because you didn't want two fractions. One of the things that you can do is the opposite as breaking things up, which can come in handy. So, as you've seen in this problem. So, and in all honesty, the only reason I even knew that, like, even thought of doing that is that you only have a limited number of things you can do. You have nothing to do with division. And if we look at the rules that we have a couple with multiplication. It's like, okay, how can I change that to look like one of these kind of thing? So it's like, that's really where it's like, okay, how can I manipulate it a little bit to make it look like something I can do? All right, what's the difference in this one? There's numbers, so this is a definite integral. All right, so find me my integral for this one. All right, so we have x to the 4th over 4 minus 6x squared over 2. And we're evaluating it from 0 to 3. Since this is a definite interval, now we're going to plug our values in. So I have 3 to the 4th over 4 minus 3 times 3 squared. And then it's minus the 0 version of that, which is just 0. So, what was it? 81 over 4 minus 27. And if I remember right, this came out to be 27 over 4. Yeah, yeah. Yeah.
Oh.
Yeah. Either one of those is right. It just depends on how you want to write it. And actually, you'll notice even in the book, it goes back and forth. It just depends on how they like to write it, like what looks better. You'll see your trig functions quite often will have the fraction in front of them with when the x is, they'll have the number underneath it. It doesn't make a difference. So really the only difference between this and this is the ones with numbers you have to do an extra step. Because in essence, you still have to do this, even if it's a definite integral. So if I got rid of those numbers, I would have just taken that and put plus c next to it and been done. So it's not much else different. All right. Do this one, and then we're going to do a word problem, which is going to address your question from last week. And then I'm actually going to cover the substitution rule tonight. Remember what I said about division. We can't do division. So somehow we have to change this problem so that there's no longer division.
Negative, bring that up to a negative?
Well, then I have multiplication. Do we have rules to help with multiplication?
Go out of x and multiply the top over x times 1 over x. Does that make any sense?
That's not going to help you. If I had 3 plus 5 over 2, how can I rewrite that? I can rewrite that as 3 over 2 plus 5 over 2. I can break up the fraction, right?
Wait, where did that come from?
Gotcha.
I just made it up.
Oh.
That doesn't work that way. So this, I can do the same thing. I can do 2t squared over t squared plus t squared square root of t over
And would
t
those
squared
cancel out or no?
minus 1 over t squared.
So you'd still be stuck with a t squared.
Yeah, but now I can just change it to a negative exponent.
Oh, you're right.
So this one just becomes 2.
Yep.
This one, I'm going to change the t to the 1/2. Yep. And this one, I will change the t to the negative second power.
Gotcha.
So this way I still don't have division. And now I can do my integral. This is the whole conversation I had in my meeting today. It's not the calculus that screws people up, it's the algebra. So, same concept. So I like when you're doing these to not simplify it down right away. So this one's 2t plus t to the 3 halves over 3 halves minus t to the negative 1 over negative 1. Don't necessarily, so it's like, so do, especially when you're starting, do your integration, do the integral first and then simplify. Because what happens is if you sit there and try to do it at the same time, what will end up happening is you'll either, one, screw it up, or two, when you go back to look at your notes, you're going to have no idea where the numbers came from. So the 2t stays, that's fine. This fraction on the bottom just flips over. So it's 2t to the 3 halves over 3. And then the two negatives make a positive, so that's positive, and then I can put that as 1 over t. And I'm doing this from 1 to 9. So we have 2 times 9 plus 2, 9 to the 3 halves over 3 plus 1 over 9 minus, now this one's not 0, so it doesn't actually go away. So 18 plus 18 plus 1/9 minus 2 plus 2/3 plus 1. So we've got $36 plus 1/9 minus 3 minus 2/3. So 33 minus, what's that, 6, 5/9? What's 33 ninths? 270, 297? $292 over 9. I got the denominator, so I multiplied by 9.
Wait, is it 36?
Yeah, 18 plus 18. So you had 2 times 9 is 18. The square root of 9 is 3. So I have 3 to the 3rd, which is 27. Divided by 3 is 9, times 2 is 18. Because then 27 times 2 and you divide by 3, either way, plus the 1/9. And then 2 plus 2/3 plus 1. Because of the subtraction, those signs change. So that's how I get the 33 and the 5/9. And I just get a common denominator from there. So again, the problem wasn't the integration. The integration you can do. It's all the other stuff that goes into it. All right. You asked a question last week. You says, well, your teacher always makes it so that you have to get it positive, so you have to do it in the intervals that go up and underneath. Remember that? Next problem, I'll show you when you use that. Remember I said it depends on how the question's asked? That's what the next question's going to be. All right. So one of the things that this is used for is when we're looking at distance, velocity, acceleration, those things. If you remember, velocity is your derivative of your position function. So they gave you your velocity and they want to know how far the particle has been displaced between 1 and 4. So all it's asking for in this problem is the integral from 1 to 4 of the velocity function. So when we're looking at displacement, we're looking at how far away from the beginning are you? How far away from where you started are you when you end? Yes, I know my pen's dying. Remember we were talking about batteries? Yeah, my pen's finally dying. it was funny because it happened in my class yesterday. I'm like, crap, it died. I'm like, my battery's dying. So I have to get a new battery for it, which isn't too bad. It's lasted almost 2 years. So I've got t to the third over 3 minus t squared over 2 minus 6t. And we're evaluating this from 1 to 4. So we've got 4 to the third over 3 minus 4 squared over 2 minus 6 times 4 minus 1/3 minus 1/2 minus 6. So 64 over 3 minus 8 minus 24 minus 1/3 minus 1/2 plus 6. So we've got I'm not doing this out of my head.
Why is it plus 6?
Change the sign. Because it was minus of minus 6. And this goes out to be negative 11 over 2, which is negative 5.5.
Negative 9
11 over 2. Or did I screw up typing this into my calculator? Nope, I didn't. I typed it in right. Oh, that should have been plus 1/2.
Yeah, I was like sitting here looking at it going, I don't know if I understand.
That should have been plus 1/2.
Gotcha.
So you're right, 9 over 2, or negative 9 over 2, which is negative 4.5. That's better. Now I know why you asked about the plus 6.
Yeah. Okay, that one right.
It's like that one was right. That one was right. The plus 1/2 wasn't right. All right, so if the particles typically, if you think about it moving along at negative 4.5, it's ending up 4.5 meters to the left of where you started. Okay, because so eventually it's actually going backwards. So it might be going forward at some point, but it goes backwards. So it ends up negative 4.5 to the left. The next question is the exact same question, except it's asking, what's the distance it traveled between 1 and 4, 1 second and 4 seconds? So now it's not asking you how far it's displaced, it's asking how far it traveled. So now, distance, like the actual signs matter. Okay? So when we're looking at this one, graph this. X squared, what was it? Minus x minus x. And we're looking at it from 1 to 4. So from 1 to 3, it's negative, right? And then from 3 to 4, it's positive. So when we're looking at this function, I need to, because I want to find the total distance, we're literally doing, we basically have to do the absolute value of it. So that negative is going to have to become positive. So when I'm looking at that calculation, I have to think about that as a separate part to the other one. So we're going to actually do 2 integrations in this one. We're going to do an integration from 1 to 3 of t squared minus t. And then we're going to do the integral from 3 to 4. And it's the absolute value of each of those. So this way, the value we're going to get is always going to be positive. So we can figure out exactly how far the object has traveled over that time. So if you remember from last week on or I can't remember if I talked about this Tuesday or Thursday, it was like it depends on how the question's asked, depends on what you're looking for. Since this was looking for the total distance instead of not just the displacement of it, we need to look at that. If it was looking at the total area and not just the difference of the areas, we would have to look at that separate piece. So in this case, we want to know the total distance traveled, so we have to look at it in separate pieces. We already know our integral for this one was t to the 4th over 4 minus t squared over 2 minus 6t. And we already know the 1 and the 4. We did those actually already. We just don't know the 3.
Isn't that the 3 and the 4?
No, so this one we did, this part was 4, and that part was 1. So we had the 1 part there and the 4 part there. So, but we'll do that again anyway. So I've got 3, so it's 3 to the 4th over 4 minus 3 squared over 2 minus 6 times 3. Minus 1 to the 4th over 4 minus 1 squared over 2 minus 6 times 1. minus 18.
Whenever you divide by 3.4, keep the third over 3.
You're right. Hold on. I was thinking of the other one that we did. Yes, it's all over 3. This is what happens when you don't do too many steps at the same time. Did I do 4 in the last one? Okay, no, I didn't do 4 in the last one. Like, did I do 4 in this one? I did. Okay, good. Didn't totally screw it all up. Minus. We're still working on the first one. It's 1 to the 3 minus 1 to the square root of 2 minus 6 times 1. All right, so we've got 27 over 3 minus 9 over 2
Wait, what?
minus 18.
Why did you mess up? Oh, you're kidding.
So that's negative 27 over 2. And there's a reason I did that one out separately, because we're going to use that same number in the next one. So there's no point in us not. Where?
Oh my god, okay, this is.
Oh, never mind. You just did the first one.
Yeah, I only did the first part.
Okay.
I'm being slow.
It's appreciated.
And then I have minus negative 37 over 6. So negative 27 over 2 plus 37 over 6 is negative 22 over 3. Since I do the absolute value of that, it is 22 over 3. So that's the first part. I'm just using a calculator to do all the fractions now. Now we have to do the second part of this. So we're going to do the exact same thing, except we're going to use the 4 and 3. So we have 4 to the third over 3 minus 4 squared over 2 minus 6 times 4. And then it was minus, and we already did this one. This was what, negative 27 over 2? Negative 27 over 2. So we don't have to do the 3 again because we already did the 3.
Oh my, what? Doing something. Yeah, I don't know. Are you doing something to find myself? No. Oh wait. Okay, no, this looks good. Wait, what?
I don't know. What you done?
I don't know what I did wrong. Wait,
With-
no, this looks.
With what?
Right? What the heck am I doing wrong? Why is that 27?
What, that?
Yeah, I'm doing something wrong and I don't know what.
Okay, so that was the 3.
Okay.
So 3 to the third over 3 is 27 over 3 minus 9 over 2 minus 18. And I just used a calculator. I just literally typed it all in my calculator.
Wait, 27 over 3. Oh, okay.
So this comes out to be negative 32 over 3
No, it's not 5 over
plus
3.
27 over 2.
No, that's 5 over 3.
is 17 over 6. Is my final answer. Right. So that's that. That's the second one. So my first one was 22 over 3. So I've got,
I am doing something really wrong then.
okay, so give me a minute. And then I add the 17 over 6.
You should not have done the math on this.
So 44, 54, 61 over 6. Yeah. So that's the total displacement. That's the total distance it's traveled.
I did 22 over 3, I think.
That could be it.
And now 27 over 2.
So that's literally the difference between when you'd want to split it up and when you wouldn't want to split it. It just depends on the question they're asking. So, but notice that the stuff doesn't change. It just changes where you're looking at your distances. So, but I couldn't just do the absolute value of the original function because I would have gotten a negative or 4/5, which isn't the same as that. Yes?
No, I'm still gonna.
Check your fractions. Odds are you're screwing up a fraction somewhere.
Yeah, I probably did.
So it's not the end of the world.
Okay, can you please go back?
Yep. All right, so I've got 2 options. I'm done with integration. All I've left to do is the substitution rule.
Okay, no.
And we still basically got 45 minutes before, like, I'm technically supposed to let you leave anyway. So I can do the substitution rule tonight. Does everybody have a printer? And I can just put the test online. You don't have to show up on Thursday. You can just print your test off and do it at home.
Yeah.
It's up to you guys. Huh?
Yeah.
Saves you coming in Thursday night.
Bring it to you on Tuesday?
And yeah, it's due technically next Thursday. It's due the day of the final.
Yeah.
So, does that work?
Do it.
All right.
Okay,
I'm going to open up another slide.
free.
Huh?
Oh, man.
So,
Yes.
is it the area or is it the length of the line of the curve?
It's, so when your integration is the area under the curve.
Yep. So, what was giving you?
So you got to remember, so in this problem that we just did,
Yep.
it's looking for the area under the velocity curve, which in essence is giving you the length that you traveled under the position.
Okay.
Okay, does that make sense?
Yep. All right.
So it's weird.
No, I understand it.
Because when you take Calc 2, there is a section you're going to do is literally looking for arc length. It's actually looking for the length of a curve. And that formula is a lot more complicated.
Got it.
Oh, this is awesome.
Huh?
I just realized literally every single Thursday class for this week canceled.
Nice. There you go. How's that worked out nice for you? It's getting down to the finals, and it's like a lot of times that's literally what ends up happening. All right. So if I did, so we're going to look for the derivative just for a second. So if we're looking for, so if f of x is, I'm not going to use that. Oh, actually, yeah. Let me actually use that one.
Yeah, so that's -1.
Yeah, let me actually use that one. But I might actually go the other direction for this one real quick. Because I want us to actually do the derivative of it first. So. Oh, that one's a mess. What did I have? X squared plus 1. All right. How do I find the derivative of this? Nope, this is the chain rule. How do we do it? We did the chain rule already.
Yeah, okay. So it's doing the chain rule?
Yeah.
Oh, God.
I'm going to do the substitution rule in a minute.
Gotcha.
How would we do this? How would we do the derivative of this? I want you to see what it looks like, and then I'm going to show you how to go the other direction. So remember, now we've got to do the derivative of the inside, right? So we said the u was the x squared plus 1. So we do the derivative of that, and we get 2x, right? And then if we looked at the square root of u, that was u to the 1/2, which was, oh wait, I got to remember derivatives now. Subtracts 1, so it ends up being 1 over, huh? Yeah, yeah.
Yeah, exactly.
There. And it's like, and that honestly, that's the hardest part of what I'm about to show you. Because you end up having to do both. And especially I don't know what it is. The power rule is the one that's easily screwed up. Everything else you could pretty much figure out, it's easy, but the power rule is constantly screwed up. Because one, you're subtracting 1, but you're bringing down the exponent. The other one, you're adding the 1 and bringing that exponent down. So it's like, it's too close and it's easier to screw up. So we've got that. So the derivative of this is 2x. And then we times it by 1 over to the square root of 2x plus 1. So if I was to make this nice and clean, I'd have x over the square root of x squared plus 1. All right. So remember, integration is going the other direction, right? So if I wanted to go from here back to here, this piece kind of looks similar to that. It's just kind of going up top, which kind of makes sense with the power rule. But I have an extra x here. Okay? That's the piece that kind of screws things up when we're starting to look at integration. Is that we have that extra value there that I somehow have to get rid of. Okay? So that's where the substitution rule comes in. And it's in essence the exact opposite of what we were just doing. So now we'll look at that nice problem that we had before, which was similar to what I was just doing. All right. It is really easy when you're writing integration to forget that. Don't. That actually has a very important purpose, especially when we're starting to look at substitution in some of the higher degree ones. Because before, if you were looking at it, when we were looking at some of the other ones, they were there, but we really didn't do anything with them. They kind of just disappeared at the end. They're going to disappear here too, but they actually are going to be used going through. So, the use substitution or substitution rule says we're going to do something very similar to what we just did a minute ago. We're going to take this piece right here, and I'm going to make that u. So u equals 1 plus x squared. Okay? We're now going to do the derivative of it, just like I just did with my chain rule. But now I'm going to make sure I put du there, not u prime. And this is 2x. And we're going to make sure we add in dx. Okay? These two pieces right here, that and that, are important. Because now I can replace things. If we look right here, I have 2x dx, right?
Now you replace it with du.
I can now exactly replace that with du. So this square root becomes square root of u, and that becomes the du.
And now you can just add back u in, correct?
Now I can just do my derivative. What's the derivative? I mean, not derivative, my integral of this. So the integral of that is u to the 3/2 over 3/2. So it's 2 u to the 3/2 over 3.
What? Huh? Where did that come from?
Because that's u to the 1/2. Add 1, bring the exponent down. And now we're going to replace u with what we originally started with. So this becomes 2/3,
And that is just to
1
make
plus
it
x
a
squared
common-
to the 3/2. And that's f of x.
Okay. So where did the 2u flee over 2?
If you flip the
Flip the fraction on the bottom.
Okay. So that comes from 2x. And I think the reason why you made it flee over 2 is because you want to make it. No. Where does that come from? I'm not flipping the fraction, but where does the whole
Where's
thing come from?
this came from?
Not that. Not that. The 2u.
That?
Yeah, flipping the fraction. No, I meant the whole entire thing. The whole entire thing.
This?
Yes.
Well, that came from there.
Okay, now let's keep checking. Oh.
And I just flipped over the 2/3.
Oh.
Or the 3/2, sorry.
Oh, that's equal sign. It looks like times to me. I don't
Sorry.
know why.
Equals. There you go. Congratulations, that's substitution. I'm just kidding. I'm going to do some more of those problems. But that's in essence what the substitution rule is. So it actually, the one thing with integration is that they only work in certain situations. Okay? If you're looking at this, the only reason I can do this is because of that 2x. If that 2x wasn't there, I couldn't replace it. Okay? And substitution wouldn't work. I'd have to do something else, which you'll learn in another class. But because the 2x is there, I can replace that whole thing, and now all the x's are gone, and I can just deal with the u's. Because that's the goal, is to replace everything with one letter. So it's all just a u, and I can do my calculations. The reason I have to do the derivative of it is because that's literally what that means. That's the derivative of x. So when I take u, I take the derivative of it to get to u, and that's the side with the derivative based on the derivative of x. And if I went backwards, I would be able to go back to that 1 plus x squared.
Where did the u to the 1/2 come from?
Just a square root. Remember, square roots, it's just a raised to the 1/2 power. And if it's a square root, it's hard to look at it and do the power rule from it. Once you make it an exponent, you can do the power rule. All right, let's look at another one.
X to the power of 4 plus 2.
All right, so yes, step 1, find out what you want to make u. It's always going to be whatever's inside of something else. So in this case, u is x to the 4th plus 2. It actually doesn't have to be. You can actually do u substitution in a lot of situations. But typically it's the thing that's going to cause you trouble, which is the piece inside. So then du is going to be what? 4x to the 3rd. dx. Do not forget the dx. All right, so.
So I guess that turns into 4, right? Because that's the only thing left over from 3x cubed dx.
Ah, almost. So I have that, and I have that. That's that, and that's that, right? I don't have the 4. So I got to get rid of I got to move the 4 over. Because the 4 is a constant, I can do this. If it was not just a number, you cannot do it. Okay, because otherwise then I'm going to have an x with a u and that doesn't work. Okay, but since it's a 4, I can divide by 4 on both sides. And I have 1/4 du equals x to the third dx. That is acceptable. That is the only thing that you can bring over to the other side of du. Until I add a whole bunch of other rules in this place and confuse you in Calc 2. All right, so we're now going to replace. So I have cosine of u and then 1/4 du. So the 1/4 can come out in front. What's the derivative of cosine? The integral of cosine. Sine. So it's sine of u plus c. And then I have the 1/4 sine of x to the 4th plus 2 plus c. You always have to go back to the original. All right, you always have to go back to that original x in your final answer. All right, your turn. Try that. All right, so what's my u? Yep. So du is? Yep. I don't have a 2 here, right? I got to bring it over. So 1/2 du equals dx. So then I have 1/2 u to the 3/2 over 1/2. Oh, sorry, over 3/2. So we get u to the 3 halves over 3.
How do you get that? Because I thought you put keychain flip.
Yeah,
Is times 1/2?
yeah.
Oh.
So then I just change it back to my x. And that's my answer. You could have done the 1/3 in front if you wanted. Sure, you can go whenever you want. Whenever you want. One wonderful thing about college, you never have to ask. Oh my God. Some people want to make their lives too difficult. Those are the people who have never taught high school. Like, this is a dream. I don't have to worry about those things. I'm not worried about those things. Oh, you're still writing? I go back. All right, 2 more problems. All right, do that one for me. All right. One of the things, remember the whole thing we were talking about with the chain rule? It says like there's certain things that once you start doing them enough, you'll start to see patterns that you don't necessarily have to do that stuff, but you know that's going to be the number there. U substitution is very similar to that. If we looked at like the last couple problems here, we know the derivative of that's 1/2, or is 2, right?
Yeah.
So I can just pull that out as a fraction. If we look at this one, this one here, remember I pulled out basically the 4th. This one's not as obvious as these 2 are. This one, that 5x is what I'm going to make it. I don't have a 5x there. So I don't have a 5. So I know I'm going to have that 1/5. So that u was 5x. So du is 1, or is 5 dx. So that becomes the 1/5 du. So once you start looking for those things and notice it's just going to be a number, you can just pull out that fraction and the other stuff just stays the same. And e, remember, e to the x is just e to the x. So this one doesn't actually change. That's how I was able to just go directly to that without really doing anything. Because if I did the integral of e to the, or 1/5 e to the u du, that's just 1/5 e to the u, which is e to the 5x plus c. So you want to start to get to look at those things like, okay, how can I just do that? Get that answer there. Is the substitution rule that difficult? It's more difficult than the other stuff, but it's not. The hardest thing is realizing that you have to do derivatives and integration at the same time and not screwing them up. So that's the number one mistake that people make when they go, especially, which you're going to see in the next problem when I do a trig one, with the sines and cosines and how they switch signs. Like, that's a really easy mistake to make when you're doing the derivatives. So let's look at this one. The integral of tangent of x. So in all the substitution rules we've come up with so far, we had to have something else to replace that had to go with the dx, right? So if I just took the derivative of tangent of x, I'm going to have something else left, right? That's what secant squared x. I don't have a secant squared x in this problem. That's not going to help me. So if we go back and look at our rules from the very beginning of the beginning of class, you'll notice there's no integral of tangent. So how can we do it? Huh? You know. So enlighten them. How should we do it?
Well, tan, you can break it up into smaller pieces that are could do things with actually.
Okay, so what's tangent break up into?
Sine of x over cosine of x. Start that.
So if I now just change this to sine x over cosine of x.
Something has been tried at least.
Yes.
But now we have an extra piece. We have two things to work with.
We do. And the substitution rule needs one of those things. So we replace something and we need something, right? So what do you want to make u?
Sine of x.
Okay. Believe it or not, it doesn't matter. So u is sine of x. So du is? Oh, actually, this is going to be harder for you guys because you don't have the rest of the stuff. Cosine of x dx. All right. Do we have cosine of x dx? I forgot. You guys don't have the other stuff to be able to do this problem this way. You could do this way. It's just there's more steps to it. Do I have cosine of x dx?
Yeah.
No, because cosine's on the bottom.
Yeah, no, you're right.
So I'd have cosine negative 1 of x dx, which isn't technically cosine of x. So not quite. But if we did it the opposite way, if I made my u cosine of x, what's my du? Almost. Negative sine of x dx. I do have sine of x dx. I just have to move the negative sign over here. So I now have negative the integral of 1 over u du.
Is that the answer?
What?
Or you're showing on a different,
Oh yeah, this is a different problem. That's the answer to that one.
oh, gee,
I'll go back to that one after for you. All right, so what's the integral of 1 over u? Yes. And this one, you actually have to put the absolute value in there. Why do I have to put the absolute value in there? Right, because I can't do the natural log of a negative number, and cosine becomes negative.
Yep.
So the absolute value is actually important. Yes. So sometimes you have to move things around. And the nice thing is that now, remember all those rules and stuff that you had? You now actually have the integral of tangent of x. You now have the answer for that. So if you ever see the tangent of x as an integral, that's the answer. So you don't need to necessarily do the chain rule, the substitution rule, if you already have the answer for it. That's integration. At least the beginning of it. There's still another chapter 6, 7, and 8.
That's next semester, right?
That's next semester. Yeah, so Calc 2 covers